What causes vanishing gradients in deep learning models? Imagine trying to teach a robot to recognize faces, but every time it learns, its early lessons seem to fade away. That's similar to what happens in deep neural networks when gradients vanish. When training these models, we use a process called backpropagation to update the weights. Think of backpropagation as a way to send signals backward from the output layer to the earlier layers. These signals are called gradients, and they tell the network how to improve. But sometimes, these signals get so tiny that they almost disappear before reaching the first layers. This is what we call the vanishing gradient problem. The main reason this happens is because of how gradients are calculated during backpropagation. When a neural network has many layers, the gradients at each layer are found by multiplying derivatives from the layers above. If these derivatives are less than 1, which happens often with certain activation functions like sigmoid or hyperbolic tangent, then multiplying many small numbers makes the overall gradient shrink exponentially. So, the earlier layers get tiny updates, making them learn very slowly or not at all. This means the network struggles to learn complex patterns because the early layers don't get enough signal to adjust properly. Activation functions play a big role here. Functions like sigmoid and hyperbolic tangent squish input values into small ranges, and their derivatives are between 0 and 1. This causes the gradients to shrink during backpropagation. On the other hand, activation functions like rectified linear unit, or ReLU, have derivatives of either 0 or 1. This helps keep the gradients stronger and prevents them from vanishing too quickly. The depth of the network also matters. The more layers there are, the more times the small derivatives are multiplied together, increasing the chance of the gradients vanishing. Poor weight initialization can make this worse by starting the network with weights that cause the gradients to shrink rapidly from the beginning. This problem makes training slow and can cause the network to get stuck in suboptimal states. It limits the model's ability to learn deeper, more complex features. To fix this, researchers and engineers use techniques like ReLU and its variants, which help keep gradients alive. Batch normalization is another method that normalizes inputs to each layer, making the training process more stable. Residual connections allow the gradients to skip over some layers, reducing the chance of vanishing. Proper weight initialization also helps by setting weights to values that don't cause the gradients to shrink too fast. Understanding why vanishing gradients happen and how to prevent them is key to training deep neural networks effectively. This knowledge is essential for developing advanced artificial intelligence systems like ChatGPT, DALL-E, and Midjourney, which relying on deep learning to understand language and generate images. When gradients flow smoothly through all layers, these models can learn richer representations and perform complex tasks more reliably.